Welcome back, everyone. Welcome back on this ICAI Day, the autumn edition. Welcome to the online and offline crowd. We continue with the presentation by Weiyi. He will talk about the graph attention networks, and he is ready at this table to present. Again, first a presentation of about 20 minutes, then airspace for Q&A. Please give him also a warm welcome, Weiyi.
Thank you, and welcome to my presentation. My name is Weiyi, and I'm currently a PhD candidate from Radboud University Medical Center. In this work, I work with my colleagues, Dr. Colin Jacobs and Dr. Bram Verheniken, and also Dr. Jean-Paul Charbonnier from Sirona, which is a company that specializes in medical imaging research. Today, the topic of my presentation is about airway labeling in CT scans using graph neural networks. So in this project, the collaboration between Radboud and Sirona is under the framework of the Siro Lab, one of the ICAI lab here in Nijmegen. In this collaboration, Sirona helped me with the data annotation. Also, we have lots of fruitful technical discussions. I don't have any disclaimer. And the outline of this presentation, it will be 4 parts. First, I will introduce you the problem, what is airway labeling, and how it can be used for the COPD treatment. And second, I will introduce, just give you the brief introduction about the graph neural networks with a simple example and how it can be used for the node classification task. And then I will move on to our methods and how we use graph attention networks for labeling airways. And in the end, we show the result and discuss future directions. First, let's talk about this chronic obstructive pulmonary disease, which is a disease that we are dealing with in this project. It's a disease that kills more people than most well-known cancers. It's basically a COPD is an umbrella term for most commonly 2 types of disease. One is chronic bronchitis, where you have this thickened airway walls and also smaller the airway lumen sizes because of the inflammation. The second is emphysema. Okay, usually in COPD, the patient will have difficulty in breath because a part of their lung is damaged in the case of emphysema, meaning that the functional unit in the lung that are responsible for exchanging oxygen are no longer working properly. Probably caused by the smoking. It's a smoking-related disease, also by some underlying genetic factors. And because the lung are damaged and the airflow in those damaged regions are limited, and there will be lots of trapped air in the patient's lung, and the patient will feel that their lungs are inflated, so that they have to try harder to breathe. That's a problem with this disease. So one of the treatment for the severe COPD, severe emphysema case, on the left side image, you see that this patient on the right side of the lung, because this is actual slice of the CT imaging, is mirrored. Actually, it's on the right side of on the right lung, but it's shown on the left side. So on the right lung, we have this we have lots of emphysema, showing as darker regions in this image. And to treat this case, we can place, one of the treatment options is to place the one-way valve here on the airways that leads to that region, the target lobe, usually, which is the lobe we want to treat it. And because this one-way valve only allows the air flows out, not flowing in, so as patient breathes, this part of lung will eventually collapse. That's the ideal outcome of this treatment. I really like this treatment because it's much less invasive than the lung volume reduction surgery, which is a major surgery that, especially when the COPD only affecting older populations where those people already have bad health conditions, a major surgery can cause many complications and sometimes mortality. Now we know the COPD and the valve treatment. But before we go into the valve treatment, we have to answer several questions, and these are some of the questions, but not the full list of questions we need to answer. One important question is that whether there is a collateral ventilation or not, meaning, so in the case showing on the left side of the image, if you want to treat the left lower lobe, I don't have a pointer here, but if you see there are two lobes here, upper and lower. If you want to treat right lower lobe by placing the valves on the the small airways indicated by those red dots, allow the air only coming out, not coming in. But this is not going to work because there is a backdoor pass between lower lobe and upper lobe. That's called collateral ventilation. Eventually, this lobe will not collapse. And that's why in my PhD, I designed a lobe segmentation algorithm so that we can, once we segment the lobes, we can compute the features and then measure the feature completeness to know if there is a hole, in the imaging to determine whether there is a collateral ventilation or not. And second part is we can perform airway analysis, right? We can measure the airway, for instance, the luminal diameters to know what size of valve we need to put in. And the more advanced approach that we want to perform airway labeling in order to perform a regional airway analysis. So we want to compute those measurements on a specific anatomical branch. And airway labeling can also be used in many applications. For instance, we can keep track of the airway shapes before the treatment and after treatment to monitor the condition, the airway condition. Also, airway labeling can be used in, for instance, virtual bronchoscope to actually know where you are when you do the bronchoscope, when you don't have the full view of the airway tree. So that's how airway labeling and others can be used in this valve treatment. And now let's talk about airway labeling. And so I can think of airway labeling as airway as a tree structure where the trachea is a root node on top of it on the right side of the image, and the trachea will lead to two main bronchi, left and right main bronchi. That leads to a different part of lung because we have two lungs, and these two main bronchi will lead to further to the lobe-wise bronchi. So human beings have five lobes. Right upper, right middle, right lower, and left upper and left lower. And each lobe bronchi will further lead to segmental branches, which is RB. For instance, for right upper lobe bronchi, we have RB 1, 2, 3 as segmental branches. On the left side of the image, we see that actually the focus of this project is we want to label the 18 segmental branches. That is, indicated by different colors on the right image, on the left image. So on the right side we have RB 1 to 10. On the left side we have 8 segmental branches. The difficulty of this problem is that we have high degree of anatomical variations across different subjects. So in the case I explained before, for instance, the right upper lobe bronchi, whether it's first splits to RB1 or first split to RB2 is not fixed. So we don't know. There can be also additional branches coming out before it splits to RB1. So we don't know the depth of the tree. We also don't know how many children of each node has. So whether it's a trifurcation in the case of right upper lobe or it's a bifurcation is not fixed. That's a problem, difficulty of this problem. Then I will now spend 2 slides to explain, give a very short introduction about the graph neural networks, and with a simple example. So in this case, I tend to think about graph neural network as messaging passing in graphs. So in this case, the node and edges in the graph are represented by their embeddings or feature vectors in the terms, in the graph neural network terms. In this case, if we want to update the node features for the node in the center, which is node 1, colored in green, we can simply, using the neighboring node, collect the messages from neighboring node, then update the state for node 1. By defining 2 types of functions. First is a messaging function, which is saying basically what message you want to send from nearby nodes to the node 1. And second is the aggregation function, which is basically to define, okay, once you receive the message from nearby nodes, how are you going to do about it? How are you going to merge it? In this simple case, the messaging function we basically design is a linear transformation matrix using parameterized by the matrix W here in the equation in the center. So that's a messaging function. So basically we're sending the messages saying that, okay, just give me the linear project version of your node embeddings. And once we receive that message, the summation function is the aggregation function. Okay, we just simply sum it together. So that's just one simple layer of a graph neural network, right? In this simple case, we only use one hop neighbors, so it's only the neighbor with distance 1. And we use this permutation equivalent aggregation function, which is a summation function. So in the general term, we can define any graph neural network layer with only messaging and reduce or aggregation function as shown in the equation below. In this case, we also don't consider edge features. We only consider node features. So once we know the graph neural network in basics, we show in this slide how it can be used for node classification. In this example, the input feature vector for each node is basically a 5-dimensional vector, right? And the task of this graph neural network is to assign binary labels for each node. So that's the output for this single layer graph neural network. In this case, as I showed before, we still use very simple linear transformation matrix as the messaging function, and we still use a summation as the aggregation function. But in the case to do binary classification, we make the linear transformation matrix W to be, in this case, 5 times 2 matrix. And so in the end, after this layer, the embedding output, H1 output, will be a 2-dimensional vector, which then you can train this network with binary, cross entropy with the ground truth labels. And that's the idea of the node classification. So now we know how a graph neural network works and how it can be used for node classification. We tend to think Airway labeling as a branch or node classification problem, where the Airway tree is a graph, and we just want to assign labels to each of the branches. Here in our case, we designed this kind of two-stage approach. The first, we need to extract the node features, right? In the previous example, in the node classification, the input to the graph network is the node features. So we use a convolutional network to extract the features for each branch, and then this feature will use as input to the graph neural network to predict the probability of a branch to one of the 22 class. Why is 22? Because we have 18 segment of labels, and I added 3 additional labels for make training easier. That is trachea and the left 2 man bronchis. And then we have a background label for the rest of the Airway tree. So in the end, we have a 22 dimensional one-hot encoding vector for the reference labels. Our dataset, we use COPD gene study, 220 subjects, and we use the inspiration scan from the acquired when the first patient, during the first patient visit. It's called baseline CT scan. The inspiration scan is basically when you breathe in, and you hold on the breath and take a scan. And the Airway tree are segmented, extracted and segmented, and the anatomical labels are assigned manually by Sirona analyst. First, I explained how we extract the node embeddings, how we extract the branch features using a convolutional network. The approach is very simple, and we just use the label map as the input. So once we have the Airway segmentation, we can compute the center of each branch, use the center as the center of the 3D cube to crop a patch from the Airway tree label map. And we give different colors. For instance, the branch in the center, we give 0.9, and the rest of branches, we give 0.5. And the background, we give 0. So it's basically a label map as an input. of the size 80 power 3. In the end, after training this simple convolutional network, we have this a representation for each branch, which is 1024 dimension. That is the input to the graph attention networks. The reason why we use a graph attention network is that we want to introduce this edge weights. Not sure if you can see it on the lower left part of the slides, there is an equation where in the middle we have this EIG, that's the edge weight between node I and G. If you remember the example we showed before, when the aggregation function is basically a summation function, so we basically consider each edge equally. But in this case, we want to, do the anisotropic way, which means we consider edge differently using an edge weight mechanism, where the edge weights in this graph attention network is computed based on the formula shown on the right part of the slides. So first we use linear projected weight and we concatenate together for two connected nodes. And then this concatenation will be reshaped into a scalar using another linear projected function. So this scalar will later be, activate using some activation function. You can use ReLU. In this case, we use leaky ReLU. If you use ReLU, meaning that you want to, eliminate some weak signals, some weak similarity between nodes. With some edges you want to ignore. And in the end, we normalize this scalar using all the neighboring nodes. So this is basically called attention. There are many ways to compute this attention. This is a standard way we show here. Using this weight, edge weights, we can increase the model capacity. And that is our, I can also explain more in this case because I remember the Michael Burstein presentation, he mentioned that usually the graph neural network tend to work with shallow layers. If you design a very deep graph neural network, you end up with the over-smoothing effect. And in this case, we also see this kind of effect because we use 3 layers of graph attention networks instead of, we see worse result with 6 or 7 layers in our case. One probable reason maybe we don't have a large graph to work with, not with many nodes. This is maybe some add-on on these slides. Here we show the quantitative results. Comparing 2 different approaches. One approach is using branch features learned by the convolutional network. Another is the branch features learned by the graph attention network in classification of array branches. The 2 metrics are used in this study. First is branch level accuracy, ECC. Another is the geodesic distance, which is measuring do we have any critical error in the system? Meaning that if you label trachea as RB1, for instance, then it's as far from the target nodes, then the shortest distance will be large. We see that both methods actually have lower than 1, geodesic distance, meaning that the most errors are just 1 branch off. And we see in terms of accuracy that graph attention network is actually perform much better than the convolutional network, from the 82% to 89%. Also, we see that for some branches, the accuracy is much higher than the others. For instance, the RB6, we see the perfect score, the 100% accuracy. This is actually the case because RB6 have very low anatomical variations. But LB1 plus 2 or LB3, 4 have very high anatomical variations. That's why they have accuracy around 0.8. And the qualitative results shown here with 2 columns on the right. We have 2 segmental branch results, RB8 and LB10. We have 3 rows. First row is a graph attention network prediction, and the second row is a manual annotation. The third row is convolutional network. In this case, we see that, for instance, RB10, the convolutional network is actually labeled some of the child as RB10 as RB10, but they actually labeled LB8 and 9 correctly. And in this case, graph attention network fix the problem, because once you know the LB9 and 8, you can infer where is RB10 based on the captured local network structure. The last slide I showed that we also plot the features in high dimensional using TSNE plot, which is a way to plot high dimensional features in 2D. What we are plotting here is that on the left is the 1024 dimensional feature vector we extract from the convolutional network. The right side image is a 1024 dimensional vector extract from the graph attention network. We see that in this case, on the left image, the LB7 and LB10 is actually isolated from the LB8 and 9. But they're supposed to close each other because they're connected close to each other in the array tree. But this is not happening in the graph attention network, because the RB7 to 10 are clustered together close to RB6 because they're all from the right lower lobe. They're all right lower lobe segmental branches. This is a sign that actually graph attention network is capturing those local airway structures. We conclude that today I showed a novel anatomical airway labeling method using graph attention networks, and our method is actually outperform the traditional convolutional network approach in airway labeling, because it captures the local airway tree structural relationships, whereas the CNN only process each branch independently. And for future research, we want to try more graph neural network structures, because last year there are some works actually trying with very deep graph network. If you're interested, there's a paper called 1000 graph neural network layers published in ICAI, yes, I remember. So we want to go deeper to see if actually it can work or not. And then we want to try with the end-to-end training with airway segmentation and the labeling. And with those algorithms, we hope that with airway labeling we can perform airway regional analysis, and eventually can improve the treatment planning for the valve treatment. With that, I want to end my presentation.
Thank you very much.
Yeah, very happy to answer questions.
Thank you very much. First practical question, how far are you in your PhD trajectory?
I'm at the final year of my PhD, so this would be my last project.
Okay. Yeah. And you finished off with the remarks for further research. What I was wondering is, airways are very specific, and at the same time they have this tree structure that perhaps also blood vessels have. Do you think that it can be more or less, the technology can be copied?
Yeah, exactly. I think there are already some works are published about using this kind of technique for vessel classification. Okay. Yeah, vessel labeling, whether they want to see if this. Also, I think it's in the chest region, also from the chest CT analysis.
So
there is already work being done there.
Okay. That's wonderful. I would like to see if there are any questions from the audience here or online, and I will come to you with a mic so that everyone also online can hear you. It's different than online. So it's fun. Your name, please, and your question.
Hi, my name is Thijs. I was wondering, the data that you're working with is a very specific type of graph structure, as it is directed and a tree-like structure. I was wondering if you had any ideas on using certain techniques to make use of this partial ordering for better results.
Yeah, good question. Actually, there are a lot of approach working with the tree space, like matching between the test graph with the reference graph. Searching in the tree space to find some distant metric to match that. That's one way to go. But we think this is the method we present is more generic. Can be applied in many different applications. That's why I want to go to this direction. Yeah.
Okay, we have time for 2 more questions, online or offline. I'll come to you for your question. Also, your name, please, and the question.
Thank you. Hi, my name is Maurits. Just one simple question. Is the graph you use directed or undirected?
Yeah, undirected.
Okay.
Actually, bidirectional.
Yeah, okay.
Yeah. So actually, I tried only the from the top to bottom, one-way tree graph, but the result is not good.
Oh, I will come back. Wait a second.
I hope that answered the question.
But if you do it only one directional, then there is no message passing going on anymore, right? Because you just have one path.
Yeah, you have to design in a way that there is a loop. Otherwise there will be some information explosion for certain nodes. Because that's also, I think that's also one of the reasons why the graph network is not going deeper. Because if some nodes are really important nodes, then you have lots of connections. Then as you iteratively have these layers, a very large number of layers, then you have this information kind of explosion for certain nodes.
Yeah.
So you have to carefully design your tree, your graph.
Let's see if there is one final question live or online. Let's see. If there is no final question, then I would like to ask a more reflective question that also is a nice bridge to the discussion, because we will discuss the ICAI labs and also how the scientific institute and the corporate reality, how it influence each other. In your case, it's the medical environment. What did you learn about the topic that you're studying that you find fascinating?
Yeah, it's actually through lots of discussions with a company called Sirona, because they are actually facing the real-world problems that they have products, working with in clinics. Yeah. That's why I understand this problem, why there are so high anatomical variations for certain branches. This is really a good collaboration in terms of Sira Lab.
Okay, and after your PhD, will you stay connected to this field, or will you go completely different?
Probably I will.
Okay.
Yeah.
Okay. Thank you very much, Chair Weiyi, for your presentation and your answers. Please give a big round of applause. Thank you.